Good evening, everyone. Welcome to the St. Albert the Great Forum on Science and Religion, which is one of the program that the Cornell Catholic community puts together. I'm Jonathan Lunine. I'm your speaker, but because I help organize this program along with Father Jerry McCune, who's sitting over there, and Eileen Heptig, I get to introduce the series, introduce myself, and give the talk. So before I do that, this is an unusual venue for this forum. We've been having them over in Annabelle Taylor. Was thought that this might actually be a better place in terms of the AV, which it actually is. And so I want to thank Mary Mulvannerton, who's the Associate Director of the Cornell Center for Astrophysics and Planetary Science, which I direct, for organizing this and getting the room open, and organizing also, I guess, do we have refreshments? We do. We do. We have refreshments. Okay. If we didn't, I was going to say, and for deciding we didn't need refreshments, but we actually need refreshments, so she's put that together. And I want to thank Eileen Heptig, who does the logistics for the posters and advertising. Want to also thank the Chesterton House, which has co-sponsored this event tonight. And I want to thank Bez Thomas for staying here late and running the audiovisual. So the purpose of this series is to host talks on the nexus, the intersection of science and religion. We've had a variety of these over the last year, and we hope to have more coming up. So if you have an idea for a talk in this series, please email, let's see who's on the email list here. Just email catholic@cornell.edu and indicate it's the St. Albert the Great Forum. Or you can email me, and you'll be able to find me on the just in the university directory. So I'm a professor here at Cornell in astronomy. Also, I'm a member of parishioner at St. Catherine of Siena, Roman Catholic Church here in Ithaca. But I help out and from time to time go to the masses at Cornell Catholic community as well. And my interest in Father Georges Lemaitre comes in two ways. One is he is a dramatic example of somebody who not only pursued a life of science to great success, but also a life of faith, and who literally wore his religion on his sleeve or on his collar in his case. And so the public persona that he was, somebody who was both a Catholic priest, a religious man, and a scientist, affected the interaction he had with the community that he did his work in, which was the community of cosmologists of the 1920s through the 1940s. But his story is also a very interesting one about scientific credit and how there's a very contingent aspect to getting credit for things. Actually, his reputation in the field of cosmology has waxed and waned. He was remembered through the 70s. In fact, the textbook that I used in general relativity when I took that class back in 1980 at Caltech had a whole appendix which included several pages on the Lemaitre metric in cosmology, which I'll explain. By the 1990s, 2000s, he was forgotten. And a general relativity textbook, which I also own, because it was sent to me by a publisher who I was writing another textbook for on an unrelated topic, but who wanted to show me that one could have great success in using only black and white images when I wanted color. That textbook entirely ignores Lemaitre. He's nowhere to be found. And in the last 10 years, his reputation has been, I would say, repaired to the extent, as far as I can tell, that he now has more or less the reputation he deserves, although I'm going to suggest one more recognition. So without further ado, let me first tell you that if you're interested in this topic some more, there are two books. I mostly use original papers and historical papers written about him. But there are two books, one published in the 1990s, The Day Without Yesterday, about Lemaitre, and the other, a brand new book, quite a bit longer, The Atom of the Universe, Life and Work of Georges Lemaitre, I actually haven't had a chance to fully digest the right-hand book. I do prefer the left-hand one. It's shorter, and I think it's more not only incisive, but more thoughtful about his contributions, but both books are good. So let me begin with a prologue. It's fair to say that the dialogue between science and religion has become something of a lucha libre wrestling match, thanks to the amplifying effects of the internet. And one need not go very far into the internet to find outrageous claims by people both from the side of those who would take the Bible literally and argue on the basis of that global warming can't possibly happen, or that the earth is young, or that evolution doesn't actually work, and so on. And you can find quotes by people on the other side, scientists, prominent scientists, who declare, for example, that science has shown that free will is actually an illusion and does not exist, which is the greatest gift to defense attorneys that anyone could ever provide. But Cornell has a distinguished history in this battle, because our very first president, Andrew Dixon White, wrote a fairly well-known treatise in 2 volumes entitled The History of the Warfare of Science with Theology and Christendom. And in fact, he dedicates this book to the memory of Ezra Cornell. Now, every student in this room should know that White was the first president of Cornell. He was a young man when Ezra Cornell was an old man. And Ezra Cornell donated the land and fixed things up in the legislature to make Cornell possible, and White was the president. Well, this book is very entertaining. It is written in a kind of a breathless fashion. Here's one example about Galileo, how semi-scientific professors endeavoring to curry favor with the church attacked him with sham science. Earnest preachers attacked him with perverted scripture, whatever that means. Theologians, inquisitors, congregations of cardinals, and at last 2 popes dealt with him and, as was supposed, silenced his impious doctrine forever. The whole book sounds like this. And so if you want, if you want to get your heart racing, read this book. It's a little light on the history side, but nonetheless, it's very entertaining. But against all this rhetoric stand a few people who led very quiet and very fruitful lives in both science and religion, and one of these is, in fact, Lemaitre. So I want to start by introducing him. A very sketchy biography of him is that he was born in 1894 in Charleroi, Belgium. He was educated at a Jesuit high school. He said that at the age of 9 he knew he wanted to go into the priesthood, and as he did his high school education he knew he wanted to be a scientist as well. So he obtained a PhD in mathematics at the University of Louvain in 1920. Between that and his PhD in physics at MIT in 1927, he was ordained in 1923. He then got permission to go to the United States because he was offered a position actually to work at Harvard with Harlow Shapley, who was a famous astronomer. But because of the arrangement, his PhD was actually at MIT, which was also in Cambridge, or across town essentially in Cambridge. And so he was given permission. He went to the United States. He got his PhD in MIT and became a professor at Louvain in 1927. In 1934, after writing several rather remarkable papers, which I'll talk about, he won the highest scientific prize in Belgium. He was nominated by Albert Einstein, but interestingly, this prize, the Franqui Prize, was actually, at the time, the second most lucrative scientific prize that you could win other than the Nobel Prize. So it actually made him relatively well off at that point. He then was awarded in 1953, well after he stopped his work, the Eddington Medal of the Royal Astronomical Society. He was elected to the Pontifical Academy of Science, which is an Academy of Science of the Vatican. By the way, you don't have to be Catholic to be elected to it, but you do have to be like Stephen Hawking because he's a member. And he became the president of that academy in 1960. He retired from teaching in 1964, and he died in 1966. So already you see a remarkable biography. But what's really interesting about him is his role in cosmology. And you have to start about 10 years before he actually wrote his papers with the year 1917, which we celebrate today as the year that Einstein published his theory of general relativity. General relativity is 100 years old this year. And when Einstein developed this theory, which was essentially a beautiful work of mathematics, the understanding of the universe was very primitive compared to what it is today. For one thing, it was not understood whether these so-called nebulae, and this is the Andromeda Nebula, photographed in 1900 from Yerkes Observatory, whether they were systems of stars like our own Milky Way, or whether they were clouds of gas with a few stars in them embedded within our own Milky Way galaxy. And the prevailing assumption was that the universe was our galaxy, and these were embedded within that galaxy. It was in the period when Einstein did his work that observational astronomers began to realize that that was wrong. They had several tools available to determine the distances to these spiral nebulae. And by the 1920s, they had come to realize that these were actually galaxies a long distance from our own Milky Way system of 100 or 200 billion stars. But Einstein didn't know that, and furthermore, there's no evidence that the universe was evolving, so it's natural to assume that it was static, unchanging. And Einstein's theory that he had developed of space-time included the very interesting assertion that matter distorted space and time in such a way that space would become curved, space-time would become curved, as on the cover of this general relativity textbook, which is the later one that I acquired, the one that doesn't mention Lemaitre. And that curvature of space means that even light, which was thought to be impervious to the effects of gravitation and matter, is bent by the effect of the mass of bodies. And in fact, this was demonstrated shortly after the theory was published by observing the bending of starlight behind the sun during a total solar eclipse, the only time when you can actually see the disk of the sun projected against the stars in the background. But you can see this now in so many beautiful ways with images like the one at the bottom taken by the Hubble Space Telescope of a phenomenon called gravitational lensing, where a foreground galaxy, which is this bright yellow dot here, is bending the light from a background galaxy, and it's distorting it simply because the foreground galaxy is distorting the geometry of space-time in such a way that the light from the background galaxy is being curved and refracted so that it forms a ring. So this is the ring. It's called an Einstein ring. It's the image of the background galaxy. If the foreground galaxy were not there, you'd just see a normal plain old galaxy, although it would be very, very dim compared to what's seen here. It's actually magnified thanks to lensing. Einstein predicted this, but he couldn't see it. It was not something you could see with telescopes at the time. But Einstein realized that in his static universe, having matter present would cause that static universe to collapse because matter bends space-time. And so in order to avoid that from happening, he introduced a term into his field equations for relativity called a cosmological constant, which was basically just a factor that adjusted the geometry in such a way that the curvature of space and the cosmological constant would balance the effect of matter, and the universe would remain poised in this unchanging state. It would neither collapse or expand. A contemporary of Einstein, Wilhelm de Sitter, who immediately understood general relativity when he read the papers, adopted a different solution to this problem. He just got rid of the matter in the universe and assumed that the universe was empty of matter, and he then showed that Einstein's equations without a cosmological constant would give you a static universe, with the inconvenience that there was no matter in it. But it was a kind of a limiting case of a very, very low density universe. Now, neither of these solutions was particularly satisfactory, but a few years after Einstein published his paper, a Russian mathematician, Alexander Friedmann, came up with a wide range of solutions to the field equations of relativity, with all sorts of different curvatures of space and geometries, including some that were collapsing and some that were expanding, and they had matter in them. And there was no need for a cosmological constant. Friedman was very isolated from the rest of the world. He was in the young Soviet Union. He couldn't travel. He didn't have access to a lot of journals, and he wrote his material down in very obscure publications that were not known to other cosmologists working at the time. Einstein knew about them, but Lemaitre apparently did not. And Friedman furthermore died in 1925, 3 years after he started working on these solutions. So other than the fact that he published these mathematical models that showed that in fact you could have an expanding universe with matter in it and be consistent with the theory of general relativity, he had no contact with the astronomical data of the time and no correspondence with people. And so in 1925 and 1927, Lemaitre, in the course of doing his thesis, produced solutions to the field equations that allowed also for an expanding universe with matter, apparently unaware of Friedman's work. But more importantly, he was stimulated by, and he applied it to the data that were becoming available about the cosmos about a decade after Einstein had published his static solution and de Sitter had published his empty universe solution. And the kind of data that Lemaitre began to have access to was, number one, distances to other galaxies, and some of Lemaitre's doctoral work actually was involved in working that out, and also data on what's called the recessional velocities of galaxies, the speed at which galaxies were moving, in fact, the majority of them away from us. And that could be measured by looking at the shift in light, the wavelength of light, as galaxies receded. The wavelengths of light would be shifted toward the red, an effect called the Doppler shift. But what Lemaitre recognized was this was not galaxies moving through an empty space. It was the space-time itself expanding. That is, it was the expansion of the universe. And that's what stimulated him to publish those solutions. So Lemaitre's approach, and this is him at Caltech with Einstein, his approach differed entirely from Einstein and Friedman in that he was using galaxy data from observational astronomers, Edwin Hubble in California, and Vesto Slipher, who was one of the best names for an astronomer I can imagine. His middle name was Melvin, and he preferred that, but Vesto is so much better. Working at Flagstaff, at the Lowell Observatory in Flagstaff. And what Lemaitre deduced was that the speed of galaxies was proportional to the galactic distance. The farther away the galaxy was, the faster the galaxy was moving. Now, he derived that as part of his analysis of the data and his solution to the field equations. But that relationship is called the Hubble relationship. And the constant, the proportionality constant between the speed of the galaxy and the distance to the galaxy in this expanding cosmos, this expanding space-time, is called the Hubble constant. It's given, by the way, in kilometers per second, which is the recessional velocity, per megaparsec, which is the distance unit. That's 1,000,000 parsecs. A parsec is 3.26 light years. It's derived from the angular shift in stars that you see when you measure their distance by parallax. That's a technical point, but I want to make that point because you'll see those units a little bit later in a paper by Lemaitre. So the key is that Lemaitre realized that in a homogeneous, uniformly expanding universe, there would be this kind of proportionality constant. If you imagine a loaf of raisin bread, and suddenly it starts to rise because of the yeast, it expands, then any particular raisin is going to see every other raisin moving away from it. These are intelligent raisins, or raisins with astronomers on them. And furthermore, the farther away a raisin is from your raisin of interest, the faster it's going to be moving. Because if it's 4 centimeters away and the whole thing doubles, it's now 8 centimeters away. But if it's 10 centimeters away before it doubles, now it's 20 centimeters away. So the velocity then is just proportional to the distance in this uniformly expanding space, which in this case is a piece of raisin bread. You can play the same game with a balloon, although a balloon is more curved than our universe. you blow up a balloon and put dots on it, the surface is the two-dimensional analog to our universe. As you blow it up, you can measure distances to galaxies and convince yourself that this relationship really does work. Hubble published this relationship in the Proceedings of the National Academy of Sciences in 1929. And not only is H known as the Hubble constant, but astronomers are so thrilled with Hubble that the Great Space Telescope, Hubble Space Telescope, carries his name. But in fact, in 1927, Lemaitre published the same relationship. And he published it in French, and he published it in a Belgian journal. Now, any graduate student of astronomy here today would know that that's not the way to get your H factor up. But even at the time, even though French was more important as a scientific language, it wasn't very important in astronomy. And furthermore, he didn't publish in Paris, he published in Brussels. So the paper was entitled A Homogeneous Universe of Constant Mass, an expanding universe of homogeneous universe of constant mass determined by the radial velocity of extragalactic nebulas. And Hubble's constant is in there. It's not called Hubble's constant, and that was published in 1927. So as Robert Kirshner, an astrophysicist at Harvard, pointed out in 2009, Lemaitre had worked it all out, but he did it publishing in an obscure journal. And that's why this is not the Lemaitre Space Telescope or the Lemaitre constant. As Kirshner said, it seemed to be a fatal mistake. So we don't know why he did that, except he was teaching at Louvain, which was in Belgium. The story would have ended at this point were it not for a mistake that one of his mentors made. So before he went to Harvard and MIT, he did some work in the UK with Sir Arthur Eddington, a prominent astrophysicist there. And he had been working with Eddington. And then in 1930, Eddington gave a talk at a scientific conference in which he displayed his new solution to Einstein's field equations, an expanding homogeneous universe, which was actually Lemaitre's solution. A student or a person in the audience recognized this, wrote to Lemaitre. Lemaitre wrote back to Eddington and said, you know, I did this, don't you remember, it's in my 1927 paper in French in Brussels, but he knew that Eddington had read it. And Eddington went back and realized what he had done and was deeply chagrined. So he was not trying to steal Lemaitre's work, he had just simply forgotten. And this happens to all of us. And as soon as he realized that, he wrote to Lemaitre and he said, we have to get this paper published in English. And so he arranged with the editor of the monthly notices of the Royal Astronomical Society to have the paper published in English. And here it is, and there's the same title, but in English, An Expanding Homogeneous Universe of Constant Mass, Counting for the Radial Velocity of These Galaxies. And all was fine and good, except that the Hubble constant wasn't in there. So in fact, if you go to the original French text, you see that Lemaitre had written in 1927, 2 years before Hubble, utilizing 42 of these nebulas derived from the list of Hubble and Stromberg, and taking account of their proper motion of the sun, which he gives here in the sun's direction, one finds a mean distance of 0.95 million parsecs and a radial velocity of 600 kilometers per second, and therefore 625 kilometers per second per million parsecs. That's the Hubble constant, okay? And he had derived that, but it's not in the English language version. So the omission of this was a mystery for many decades. It was unexplained except by conspiracy theorists who said that, Eddington had it in for Lemaitre, or Eddington conspired with Hubble because they didn't like Catholic priests getting all this stuff. It was all wrong, actually. By the way, Eddington was a Quaker, as it turned out, and a fairly devout one. In 2011, Mario Livio, who's an astronomer at Space Telescope and has an interest in history, went through the Royal Society files to try to find the answer to this. And he did find the answer. He found the letter that Lemaitre had written to the editor of the journal at the time that Lemaitre sent the English language manuscript to him. So it was Lemaitre who did the translation himself. It wasn't that Eddington had the paper translated. Lemaitre did the translation. And in his letter to the editor of the monthly notices, who had the appropriate last name of Smart, Dr. Smart, 1931, he says that Lemaitre says he found it advisable not to include what he called the provisional discussion of radial velocities, which is clearly of no, he said, actual interest, but that's probably a false friend. He probably meant current interest, because in French it's actual. And then he said, I attach a French text to show you where I cut that stuff out of the paper. Basically what he had apparently done was he realized that Hubble had published this stuff in 1929. It was now 1931. There was no point in republishing that. The stuff that Hubble didn't do was the guts of the rest of the paper on the solution to the expanding universe, and that's the part that he figured would be of interest because it hadn't been published before. And so he edited himself out of any possibility of getting credit for that constant, and apparently didn't really worry about that. Now, the other irony about this is that Hubble himself actually didn't accept the expanding universe idea. He didn't understand general relativity. He wasn't a mathematician. He was an observational astronomer. He was also a tremendous self-promoter. One of the reasons why he had such a high profile was that he knew how to get influential people up to the telescope at Mount Wilson, and he became this sort of self-styled California king of astronomy. But he didn't understand the expanding universe model. He didn't understand general relativity. And so he actually doubted it. And this is an assertion by two authors in Physics Today of 2007 that Hubble never came out in favor of an expanding universe. And in fact, you can find by looking on the web, which I did, an article from the Los Angeles Times, 1941, on several issues in science, but the first of them was that this genius, I guess Californians liked using French words in 1941, refutes the theory of the exploding universe. And they're referring to Edwin Hubble, who, if you read the article, says, no, the universe isn't expanding. My data show that it's infinite in extent and is as it's always been. And so he got credit for something that he didn't really believe in. He had derived empirically the relationship that was key to this expanding space-time, but didn't understand the implications. If you go to his biography in the American Physical Society, you find that they're rather generous to him. They say in that biography, in his paper, Hubble didn't discuss the implications of what he had found, perhaps preferring to leave the interpretation to theorists, which is a very generous way to put that he didn't understand the implications of his own results. And in fact, he then denied them 10 years later. But, you know, he's an American astronomer. It's the American Physical Society, so you can kind of understand why they gave him the benefit of the doubt. Again, this would have been the end of Lemaitre. But he himself, Lemaitre, realized what the real implication was of his model. And he realized that unless you made some very artificial assumptions, the universe had to have a finite age to it. That the expansion of a homogeneous universe in space and time meant that at some point in the finite past, it was so concentrated and dense that it wasn't what we would call the universe that we know today. And he argued that this beginning was essentially a quantum state. Quantum mechanics had was developing at the time. He published his model this time in English, in a journal that most people regard as respectable, sort of, which is Nature. And at that time, letters to Nature really were letters. I mean, this was a one-column letter in which he describes this model, titled The Beginning of the World from the Point of View of Quantum Theory. He argues that everything was in the form of what he called this primeval atom. Something then happened to cause it to fragment, and space-time expands outward with matter dividing and becoming more diffuse and becoming the galaxies and stars and life. And as Stephen Hawking says in The Universe in a Nutshell, this state was called the primeval atom by Georges Lemaitre, who was the first to investigate the origin of the universe that we now call the Big Bang. So very clearly was his model. Now, he almost immediately recognized that his model had a problem, which was that the constant that he had derived and Hubble had derived implied that the universe was only a couple of billion years old. And in fact, the age of the Earth was beginning to be derived by geologists. And this time to the beginning of the universe was shorter than the age of the Earth. Now, since the Earth couldn't have existed before the universe began, he recognized that he had to abandon this constant expansion. And so he began to look at other cosmological models, which Friedman had done in 1922, but Lemaitre was doing it with astronomical data. And what he came up with in 1931 was a model in which there was a first phase of rapid expansion and then a phase of stagnation, which allowed the universe's lifetime to be lengthened to the point that it was consistent with the age of the Earth, and then a second expansion phase of acceleration. But now he had another problem. If you stagnate the universe, possibly by putting in enough matter that it just slows down, how do you get it to accelerate again? And so now he decided that he had to adopt Einstein's cosmological constant, which in the meantime Einstein had abandoned because, having read Friedman and Lemaitre's solutions for this expanding universe with matter in it, he realized the cosmological constant was a mistake. He had blown it. He could have derived that solution himself, but he didn't. So Lemaitre adopts the cosmological constant. And Einstein said to Lemaitre at the time, "Your mathematics is beautiful, but your physics stinks," because it had his constant in it. And he did use the word stink. Now, Lemaitre went further, though, than Einstein. So this is a set of equations that are sort of indexed by two parameters. So this is not just one equation. It's a bunch of equations that derive the geometry of space-time. And I have to show an equation, of course, in the St. Albert the Great Forum of Science and Religion. So this is the geometry. This is the curvature of space-time. Okay, this is essentially the curvature of the cosmic balloon, all right, which may or may not be large. Actually, space is almost not curved at all. It's very flat, but I don't want to break the balloon trying to do that. The other side of the equation is the content of matter and energy, which wants to cause the universe to collapse on itself. And then this term on the left is the geometric fudge factor. Gamma is the cosmological constant that keeps the universe from collapsing. Well, you can look at this as an artificial geometric factor, which Einstein didn't like, or you can put that on the right side of the equation with a different symbol and say that this is another energy term. It's a vacuum energy. It's some property of the vacuum, the space-time, that wants to push things apart, kind of a negative pressure. Well, this is the way this cosmological constant is regarded today. And in fact, measurements by Hubble Space Telescope tell us that in fact the universe is not expanding uniformly, it's accelerating. And that acceleration is caused by something that is given the name dark energy, for lack of any better term, but is basically regarded as some property of the vacuum that creates a negative pressure. Lemaitre understood this. This is stuff that has come up only in the 1990s, but in 1931, Lemaitre published a paper in the Proceedings of the National Academy of Sciences, the U.S., in English again, in which he talks about vacuum energy as being the source of the cosmological constant. And what he writes is that we must associate a pressure to the density of energy of the vacuum, and it has a negative sign, so it's a negative pressure. He writes, this is essentially the meaning of the cosmological constant, which corresponds to a negative density of vacuum. And as Robert Kirshner said in the July issue of Physics Today last year, Lemaitre's interpretation is strikingly modern, shockingly modern. This is more or less what we say today about the origin of the accelerating universe. So it isn't just that Lemaitre invented the Big Bang. He figured out dark energy, as at least the state that we understand it today. And then he stopped working. So he stopped working in part because of the societal fallout of what he had done. And the first part of that fallout was that a number of astronomers absolutely hated the idea that the universe would have a beginning. It just sounded so biblical. And in fact, there were astronomers who actively sought another solution that would keep the universe infinite in time, so that there was never a beginning. And the three most successful scientists to do this, who invented another theory called the steady state model, were Fred Hoyle, Herman Bondi, and our very own Tommy Gold, who is a professor here, basically created the modern Department of Astronomy at Cornell and the Center for Radiophysics and Space Research, which is now the Cornell Center for Astrophysics and Planetary Science. So, I stand in the footsteps of giants, as we all do. They thought up this model. They said, why not have a universe that never changes? It's expanding forever. And then you say, well, if it's expanding forever, the matter density is going down, it's diluting, so you'd end up with the de Sitter universe, with hardly anything in it. But what they argued in two papers was that to keep the matter density of the universe constant during the expansion would require such a trivial amount of creation of matter, something like 2 hydrogen atoms per cubic centimeter per 10 billion years, that you would never be able to see it. And basically they said matter is not conserved. In every cubic centimeter, after about a Hubble time, lifetime of the universe, boop, 2 hydrogen atoms appear. And that's enough to keep it constant. And all we have to do is figure out how to make those hydrogen atoms. So this steady state model was very attractive to a number of astronomers because it didn't require a beginning. And Hoyle himself, who was a real science showman, who had a radio show on the BBC, actually asserted that this model was one that avoided the scientists' unavoidable and unfortunate attraction to the Book of Genesis. He said on the radio, the reason why scientists like the Big Bang is because they are overshadowed by the Book of Genesis. It's deep within the psyche of scientists. Well, this was his code word for Lemaitre, because in fact, no one had called the primeval atom model the Big Bang until Hoyle did, and Hoyle referred publicly at meetings to Lemaitre as the Big Bang man. And so he was indirectly criticizing Lemaitre. Lemaitre, on the other hand, asserted, and this is a later talk in 1958, that as far as he could see, his model remained entirely outside any metaphysical or religious question. The materialists can deny any transcendental being as they like. He didn't see any relationship to religion whatsoever. And that was his position for throughout the 40s. However, that position, which seemed very reasonable, blew up in his face. And it blew up because of the Pope. It's 1951, 3 years after the steady state model came out, Pope Pius XII, who was a very well-read individual and very controversial because of things that had happened during World War II, but that's not part of this talk, gave a speech to the Pontifical Academy of Sciences in which he said that present-day science, with one sweep back across the centuries, has succeeded in bearing witness to the august instant of the primordial "Let there be light," when along with matter there burst forth from nothing a sea of light and radiation, and the elements split and churned and formed into millions of galaxies. That's great. That would work in an astronomy textbook, no problems. It has confirmed the contingency of the universe. Absolutely. No problem with that. Good for an astronomy textbook. Hence, creation took place. We say, therefore, there is a creator, therefore God exists. Not good for an astronomy textbook. Lemaitre was in the audience. He was floored for two reasons. One, apparently, was that the Pope didn't even mention that Lemaitre was the guy who invented this model. And number two, he had managed to associate this model with the Book of Genesis far more effectively than Fred Hoyle had been able to do. And so one of Lemaitre's students said that Lemaitre came back from this meeting to Louvain and walked into the class with the darkest expression he had ever seen on his professor's face. Now, it isn't that he didn't do anything about this, because he learned shortly after that that the Pope was about to give a talk to the International Astronomical Union in Rome, Italy, which is a much larger group of astronomers. They're the ones who killed Pluto, by the way, as a planet, decades later. And Lemaitre thought this is going to be the end. So he actually flew to Rome. He got the director of the Vatican Observatory and the Cardinal Secretary of State to get him in with the Pope. And whatever they said, and it's not clear what was said, Pius XII never gave his Fiat Lux speech ever again. So, yeah, it's pretty impressive. But the damage was done. And Lemaitre was always referred to as that Big Bang man by Fred Hoyle. George Gamow, another Russian astrophysicist, would run around saying, oh, the Pope said this today, the Pope said that today. Lemaitre actually retired from doing cosmology at that point. And it may be, in fact, because of the sort of public lampooning that occurred. It's not clear. But somewhere around a week before his death, Lemaitre was informed by friends that his model, the primeval atom model, was correct, and the steady-state model was wrong. And what had happened was that two radio engineers, trying to tune and clean their radio telescope, had detected this uniform background of radio radiation that was not coming from anything but the cosmos itself, and was correctly interpreted by a number of theoretical physicists who had been looking for this as the moment during the expansion of the universe when the universe had cooled enough that light could decouple from matter and move freely through space. Now, leaving aside that that's also in Genesis, God separated light from the darkness, this just proved the Big Bang. And the people supporting the steady-state model, possibly with the exception of Hoyle, just fell away from it. They just abandoned it. And so Lemaitre found out a week before he died of cancer that, in fact, he was right. Okay, so happy ending for Lemaitre. But what was his real attitude toward the two aspects of his life, science and faith? They weren't quite as separate as his public pronouncements, I think, made it out to be. Again, he did say at this Solvay conference in 1958 that his model remained entirely outside of any metaphysical or religious question. But if you go to Louvain and you go to his archives, you find an early draft of the manuscript of the Letter to Nature in which he introduces the primeval atom model. And there's an extra paragraph at the bottom of the manuscript which doesn't appear in the Nature letter and which has a pen mark drawn through it. And if you read that, it says, I think that everyone who believes in a supreme being believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding this creation. Now, he had the good sense not to send it this way because it wouldn't have been published in Nature, although you never know these days. Nature is pretty good at publishing all sorts of unexpected things. But it illustrates that Lemaitre was thinking about the implications of his model in terms of God being hidden in the physics at the beginning of the universe, because that time period, right at the beginning, the matter and energy density is so high that whatever went on to trigger the Big Bang, and today we would say, you know, whether it was sort of part of a compression and expansion cycle or a unique event or whatever, that we don't have access to it. It is hidden in the very, very exotic nature of the matter and space-time at that point. So he was thinking about that. The other thing that's interesting is something that isn't mentioned in various articles, but strikes me as being interesting, and that is that the way this letter is written, it resembles something that was written by another great Catholic thinker who lived 1,500 years before Lemaitre wrote this, and that's St. Augustine, who wrote a book, among his many books, called The City of God, in which he was comparing the very profane and corrupt city of Rome with the ideal new city of God, the New Jerusalem. But he speculated on a lot of things in that book. So Lemaitre writes early in his article, if the world had begun with a single quantum, the notions of space and time would fail to have any meaning at the beginning. They would only begin to have a sensible meaning when the original quantum had been divided into a sufficient number of quanta. So if there's only one thing, there's no way to mark time, and so nothing actually happens until you begin to divide this one thing into many things. If you go to the City of God, you find this statement, if eternity and time are rightly distinguished by this, that time does not exist without some movement and transition, while in eternity there is no change, who does not see that there could have been no time had not some creature been made by which some motion could give birth to change. Change the word creature to quantum, and it's more or less the same statement. Then Lemaitre goes on to say, if this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. Go to the city of God, not on the same page, but some paragraphs later, Augustine writes, thus assuredly the world was made not in time, but simultaneously with time. To a mathematician, a little bit before and simultaneously is sort of the same thing. One is the limit of the other. So this is the same statement. And I'm not claiming that Lemaitre was trying to force a model to fit Augustine's book. But having been educated in a Jesuit high school, he must have had this somewhere in his head. And so it must have influenced the way that he wrote that article, even though the model itself was clearly stimulated by his very deep understanding of general relativity, his derivation of the expanding universe model, and his derivation of the Hubble constant. Now, Lemaitre, again, was very, very firm about what the problems of fundamentalism and biblical literalism. In fact, he was quoted in an interview in 1934 as saying that it is utterly unimportant that errors in historic and scientific facts should be found in the Bible. The idea that because they were right in their doctrine of immortality and salvation, so he accepts what the Bible says, but he says the idea that because they were right in that, they must also be right on all other subjects, is simply the fallacy of people who have an incomplete understanding of why the Bible was given to us at all. He makes other statements like that. In another interview, he says, St. Paul didn't need to understand general relativity. He didn't understand it. He wouldn't have been given that by God because there was no reason to. So he did try to emphasize that science was the way of understanding the material world. And he accepted evolution, accepted biological evolution as well as being right. But he also accepted the Bible as the revealed doctrine of the salvation of humankind. It's just not a science textbook, and it's not a history textbook. Its dimensions are outside of that. He also said that, and this again, I think speaks to a more integrated sense of faith and science in his own personality, that while both the scientist believer and the scientist non-believer are at work decoding the palimpsest of nature, these remnant clues to what has happened in the past, the believer, he said, has an advantage of knowing that the riddle possesses a solution, that the problem posed by nature has been posed in order to be solved, and so its degree of difficulty is presumably measurable with the present and future capacity of humanity. And here he's addressing this conundrum that comes up with a very materialistic, naturalistic interpretation of the human mind as being something that simply evolved to hunt mammoths and build fires in caves. If that's the case, how can we possibly imagine, even with the tools of science, but we're building those tools, that we can understand the whole universe? It just doesn't make sense. And it doesn't make sense to a lot of people, and this is one answer, that in fact there was more to the human brain than just the evolutionary need to hunt saber-toothed tigers or mammoths or whatever. So he was obviously a very complex person, and very interesting both integration of his science and faith and also his insistence that certain things be separated. Biblical literalism had no place in his world. And he was admired by many scientists at the time. William McCrae, who was a contemporary of his but lived to a very old age, late 90s, wrote that Lemaitre was a scientist of superbly robust common sense. All of us who knew him must ever have wished we had paid attention to his ideas. And here he's referring to the fact that McCrae himself was a steady state adherent. And the irony of this is that McCrae was actually a conservative Christian who felt that the steady state model was more compatible with Christian doctrine than the Big Bang model. So it was a very interesting, different interpretation of steady state. But he was an admirer of Lemaitre for sure. And Kirshner talks about the fact that Lemaitre was a significant player in the formative years of relativistic cosmology, that his contributions were undervalued. he argues because he had stopped doing original research, and then he goes on to say because he devoted himself to other things, including matters of faith. I would dispute that. I think Lemaitre was driven away from doing cosmology because he had such ardent enemies who were great popularizers of science. Both Gamow and Hoyle were on the radio. Gamow wrote this classic book, 1, 2, 3, Infinity, which was great in its time for popular science. And Lemaitre was just a very retiring conservative individual, and he just didn't want to have to deal with that. You know, he remembered there was one time he walked into a conference, a Solvay conference, and Hoyle was sitting in the audience with a colleague, and Hoyle points to Lemaitre and says in a loud voice, everyone in the auditorium could hear him, "Look, there goes the Big Bang Man." And it was, you know, he probably just didn't want to have to deal with that. So he did other things. He was very big in bringing numerical methods to the university in Belgium. He was able to raise money for an electronic computer in the 1950s and did a lot of work to show how that could be used in physics. So Lemaitre was a pioneer in cosmology. He inferred the distance redshift relationship before Hubble did. He invented the Big Bang model, and he inferred that the cosmological constant was necessary and was probably a vacuum energy. And my view is, and I've tried this out on a few physicists now, that really his works are so important that something ought to be named after him. And an obvious thing is the cosmological constant, which has no scientist name after it like the Hubble constant does. So why not call it Lemaitre's constant? Despite his public persona being one in which science was separate from faith, his detractors accused him of proposing the Big Bang model on religious grounds simply because he was a priest. He, of course, pushed back against that. Privately, how he integrated his science and faith were much more complex than his public persona. But his battle with Hoyle and with Gamow and with the Pope, along with personal matters, the library at Louvain had actually been burned down by the Nazis during World War II. He was injured during a bombing attack. They were stuck in Louvain because they couldn't get out before the Nazis came in. All that was very traumatizing, and then right after the war he had the battle with the steady state theorists. So probably all of this drove him prematurely from cosmology. But he did make important contributions in computational methods in physics. Now, what about religion and science? Well, Lemaitre's life to me illustrates the fact that this modern, ultra-modern or postmodern view that somehow science and belief in God are incompatible, which is a very new view, really makes no sense. And it also serves as a warning for those who would, I think, overinterpret what science can do for us. There's a very interesting article in the Washington Post a few years back written by a journalist, Jeffrey Schloss. It was actually a book review in which Schloss says the wonderful thing about science is that it entails a straightforward procedure for rejecting false answers. It does that empirically, and that's absolutely correct. Science is self-correcting. That's what makes it work. But it achieves this in part, he goes on to say, by asking smaller questions. And he was comparing that to questions like, why is reality here? What is the purpose of our existence? Why are we here? And there are physical answers, but those are answers about the processes by which we got here, not why we are here. And you are free to adopt an answer which is, there's no reason why we're here, it's senseless. Or you're free to adopt an answer that we're here for the most wonderful reason you can possibly imagine. It's up to you. It's not implied by science that there is an answer that science provides. And Lemaitre made that very clear. The assertion that science does provide the answer is something called scientism, the belief that science is the only road to discovering truth. And Lemaitre's life, to me, demonstrates the fallacy of the assertion that to be a scientist, you have to adopt this scientismist view. But Lemaitre's life also demonstrates the fallacy that religion and fundamentalism are one and the same, because in fact he was a religious, but he was absolutely not a fundamentalist. And so to be religious does not give you the excuse to just deny in a dogmatic way religion, global warming, anything like that. Those are intellectually irresponsible points of view. And so, I don't know how many professors are in the audience. I'm glad I'm speaking mostly to students. But as professors, we have tremendous influence on our students. And so we ought to be thoughtful in maintaining a perspective in which different ways of knowing are honored. Too often we hear, I've heard all sorts of things. If the Catholic Church didn't exist, we would have landed on the moon 1,000 years ago. What does that mean? Another statement, as I mentioned, by Jerry Coyne, who's a biologist, is that free will is an illusion, and the sooner we adopt that point of view in society and teach everybody that that's the case, the better off we'll be. Well, I doubt that. And then you can, find the equivalent statements on the fundamentalist side. We just, I can't overemphasize this fact because I know of students, including one in high school, who decided to become a history major even though she was interested in science because her boyfriend told her that she couldn't be a scientist and believe in God. And so she didn't give up her faith, she gave up her desire to become a scientist. Now, being a historian is great, but that's not the reason for choosing it. So I hope that Lemaitre's life is a cautionary lesson to those who would get both overenthusiastic about their science or overenthusiastic about their religion, and recognize that as thinking, self-aware beings, we walk a very fine line in the way that we know things. Thank you. Okay, so I'm happy to take 5 or 10 minutes of questions, and then we'll eat the food that's in the back. Yes?
Did any of these people, most of what you talked about was the past, going back to Big Bang.
Mm-hmm.
Did any project into the future? What is the future of the universe? If it's accelerating, will it go on accelerating forever?
So, of course, people have thought about that. Thinking about the future is not as satisfying from a scientific point of view because there's nothing to test, right? You're projecting into something that you have no empirical way of knowing about, but you can't avoid doing that. So, one of the first things that came out of this expanding universe model was, is there enough matter to close the universe so that it would actually be gradually coming to a halt and then would start to come back and collapse again, and we'd have these endless cycles of time. The observations, as they got better and better, suggested that the universe was just on the hairy edge of being closed in that way versus expanding forever. So eventually it would become all dilute. And then the derivation of distances by supernovas using Hubble Space Telescope, that was where the acceleration of the universe was in fact discovered, which won the Nobel Prize in 1990, I can't remember the year. That put an end to that debate because with dark energy, because it's a property of space itself, even though the universe is expanding and so the matter density is going down with time, dark energy doesn't go down with time. It's a property of space. So it becomes more and more important, and eventually the universe will always be open, and eventually everything will become so dilute that it'll be like a de Sitter universe. And what happens after that isn't clear. There's a mathematician, Roger Penrose, who has a very entertaining book called Cycles of Time. He's a serious cosmologist, but he makes an argument that once everything is expanded to that point, he somehow manages to make that the end of one cycle and the beginning of another Big Bang, but in which the scale factor has gone up tremendously. It's an interesting book, and it reminds me of the movie The Hitchhiker's Guide to the Galaxy, if you remember the very end. Other questions? Yes?
So he was ordained in 1923 and got his PhD at MIT in 1927.
Yeah, I got a degree in math in 1920 from Louvain and then got his degree in physics from MIT.
Did he hold Mass in Boston?
Don't know. He certainly had to celebrate Mass, but whether he actually, I mean, I'm sure, and I'm just guessing now, that he was a celebrant locally when other priests needed, were traveling or needed time off or were sick or something like that. But he was not a parish priest. He did not have a church that he was responsible for. But he did become a prelate of the papal household about 6 years before his death, which was a very honorific title on the religious side.
What is a prelate?
What is a prelate? Prelate.
I'm not sure.
Yeah. It's essentially something equivalent to a bishop or an archbishop, but without being a bishop or an archbishop.
It's like an
Somehow.
honorary doctorate.
That's the most I could get, yeah, essentially like that. Mary.
So, if the Boltzmann, regarding his Big Bang theory, he didn't want the Pope to say Big Bang proved there is a God.
He didn't want him to say that it demonstrates Genesis.
Right. Did he ever, is there any evidence of him talking in private and smaller circles about what he thought actually caused the Big Bang?
Not that I know of.
So there's nowhere where he ever kind of said, well, of course we know that God created the Big Bang, or.
Well, he did say that in the early manuscript version of that Nature letter, because that last paragraph that he crossed out said that, in fact, because the matter density is so high, he said it in a more compact way, but because of that, God's essentially hidden in the physics, that you cannot, whatever sets off the Big Bang, it's inaccessible to us. And he referred to that as God being hidden in the physics.
So do you think his reasoning for not wanting the Pope to talk about this, or himself not wanting to talk about that, was because he didn't want the science diluted or not taken seriously, because people would assume he reached that conclusion for that only?
Yes, that's right. And bear in mind that the speech that the Pope gave to the Pontifical Academy was 2 years after the Steady State papers had been published by Hoyle, Bondi, and Gold. And Hoyle was already saying in his radio show and elsewhere that the Big Bang model only existed because scientists were too corrupted by the book of Genesis. And Lemaitre had, in addition to the quote I showed, which is from much later, earlier on he was saying, look, this doesn't come from the Bible. It comes from the data, which was right. But then the Pope gives this talk, and so he essentially undermined everything that Lemaitre was trying to do to reassure his colleagues that, in fact, this was a genuine scientific model. So it was, it must have been a really bad morning, that's all I can say. Yeah. Any other questions? Okay, if not, thank you all. And there are, oh, yes, Ricardo.
Thank you for pointing out that the supporters of both the expanding universe and the steady state cannot find an answer in religion.
Yeah.
However, there is a question that has bothered me from the time that I decided to become an astronomer.
Mm-hmm.
That is, if there was a creator, who created him or her?
Mm-hmm.
This is a question that cannot be answered by either science or religion.
Right. It's an unanswerable question. So God as the prime mover is uncreated. And that's the best you can do. I think you cannot go farther. And furthermore, if you're a Thomistic philosopher, you wouldn't say that God sets the universe in motion and then leaves it be. You think of God more as a playwright who has written a play in which there's a dimension of time running through the play. But it's different from the dimension of time that the playwright is in. And so, all of it is there. The characters have free will in the context of the play, but the existence of every moment and every event is being sustained by that playwright, by writing it. And that's different from saying that God is something that, strikes the match at the beginning and lights the fuse on the Big Bang. But it's much more of a Thomistic point of view of what the creator and what the prime mover actually means. And, it gets to my point that there are simply questions that can't be answered in an empirical way because they don't have to do with the material universe that we are actually in and that we experience. And one is perfectly free to say, as a consequence of that, those questions are either irrelevant, or you can say that there's a different way of knowing that requires faith or something else or insight or intuition in trying to approach those problems. But I think the one reaction to that is a mistake would be to say that science has somehow proved that those things don't exist, that God doesn't exist, or there's nothing outside of the universe, or, you know, there's a physical mechanism by which everything comes out of a lack of existence. Existence comes out of a lack of existence. Those are conceptually wrong. So let me give you one example of that. So this notion that, which Stephen Hawking has talked about, that because we understand that the vacuum state has fluctuations, and a big fluctuation could be the start of the Big Bang, that demonstrates that science has shown how you create reality out of nothing. That's fallacious, because the vacuum state is a something, right? And quantum fluctuations are something. So it's confusing. You know, if I have a bank account, and the bank account is at zero, and there are fluctuations associated either with some investment strategy or noise in the banking system, I could become rich if I wait long enough. But the bank account was there to begin with. If there's no such thing as a bank account, then there aren't going to be any quantum fluctuations. So Hawking is confusing an empty bank account with the lack of existence of anything that you could even conceive of as a bank account. And that's where I think there's a very serious mistake about concepts of creation versus the evolution of the cosmos. We can understand the evolution, but we can't understand through the methods of science where all this really came from, reality. That's my view. Okay, with that, we'll just eat. Thank you.